This video is brought to you by mywayteaching.com.
So now let us see specific heat capacity of solids. Okay. See here we can use that law of equipartition of energy to determine the specific heats of solids. You consider a solid having n atoms. Okay. Each vibrating about its mean position. Then an oscillation in one dimension has an average energy of oscillation in one dimension. It has an average of 1 by 2 into kBt. That will be equal to kb into t. In three dimensions, that average energy will become 3 into kBt, isn't it? For a mole of solid, N is equal to Na. So the total energy is given by 3 into kBt into Na, that is 3RT. Now at constant pressure, we know delta Q is equal to delta U plus T into delta V. Okay, that will be equal to delta U. Since for a solid delta V is negligible, we can say C is equal to delta Q by delta T, which will be equal to delta U by delta T, isn't it? So this table shows the specific heat capacity of some solids at room temperature and at atmospheric pressure. They have given specific heat as well as molar specific heat for aluminium, carbon, copper, lead, silver, tungsten. Specific heat of tungsten is 134.4 joule per kg per Kelvin. Highest is of aluminium, right? 900 specific heat. Now let us see specific heat capacity of water. Okay. See, we treat water like a solid. Means for each atom, average energy is 3 kb into T. Water molecule has 3 atoms, that is 2 hydrogen and 1 oxygen, isn't it? H2O. So that energy is given by 3 into 3 kb into T into Na, that is given by 9RT. Okay. In this case, we can write C as delta Q by delta T, that is equal to delta U by delta T, that is equal to 9R. This is the value observed and the agreement is very good. In the calorie, gram, degree units, water is defined to have unit, that is specific heat. That is 1 calorie is equal to 4.179 joules, and 1 mole of water is 18 grams. Okay, 1 mole of water. And the heat capacity per mole is 75 joule per mole per Kelvin. Okay, heat capacity per mole. See, however, with more complex molecules like alcohol or acetone, based on degrees of freedom, it becomes complicated. See, one thing we should note about the predictions of specific heats based on the classical law of equipartition of energy. That is, the predicted specific heats are independent of temperature. But as we go to low temperatures, however, there is a marked departure from this prediction. Specific heats of all substances approach zero as temperature tends to zero. Okay, specific heat of all the substances approaches zero. This is related to the fact that degrees of freedom get frozen and ineffective at low temperatures. So this, according to this classical physics, degrees of freedom must remain unchanged at all times. The behavior of specific heats at low temperatures shows that inadequacy of classical physics, isn't it? And it can be explained only by invoking quantum consideration, as was first shown by Einstein. That quantum mechanics requires a minimum non-zero amount of energy before a degree of freedom comes into play. So this is also the reason why that vibrational degrees of freedom come into play only in some cases. Okay. Now let us study what is this mean free path. See, molecule in a gas have rather large speeds of the order of the speed of sound, isn't it? In gas, they move randomly. Yet a gas leaking from a cylinder in a kitchen takes considerable time to diffuse to the other corners of the room, isn't it? We have observed this one. That on the top of the cloud of smoke, it holds together for hours. Even we have observed this. This happens. Why all this happens? This happens because molecules in a gas have a finite, though small size, so they are bound to undergo collisions. As a result, they cannot move straight unhindered. Their paths keep getting instantly deflected. That's the reason why they take some time to dispose. Suppose the molecules of a gas are spheres of diameter d. Okay, molecules of the gas are spheres of diameter d, as you can see. Focus on a single molecule with an average speed v. You just focus on any one of the molecule. Then it will suffer collision with any molecule that comes within a distance d between the centers. Between the centers, that distance should be d. Then only it comes into collision. So in time t, it sweeps a volume that is given by pi d square v into delta T, wherein any other molecule will collide with it. If n is the number of molecules per unit volume, then the molecule suffers this n pi d square v delta t collision in time delta t. Okay, thus the rate of collision is given by n pi d square v, or the time between the two successive collisions on the average, which is represented with tau, that is given by 1 by n pi d square v. This is the time between the successive collisions. The average distance between two successive collisions is called as mean free path. Okay, the average distance between two successive collisions. So that mean free path is represented with L. Mean free path. So here we have considered only one molecule. We have assumed that other molecules are rest, isn't it? But actually all molecules are moving, and the collision rate is determined by the average relative velocity of the molecules. Thus we need to replace V by V T. Okay. A more exact equation for this mean free path will be L is equal to 1 by root 2 n pi d square. Okay, so let us estimate L and tau for air molecules with average speeds 485 meter per second. Okay, let us see this. At standard temperature and pressure, it is given by so if we take D as 2 angstrom distance and tau as 6.1 into 10 raised to minus 10 seconds and L as 2.9 into 10 raised to minus 7 meters, approximately 1500 D. Okay, the mean free path depends inversely on the number density, and even it depends inversely on the size of the molecules. Okay, now let us take a simple problem. Estimate the mean free path for a water molecule in water vapor at 373 Kelvin. Mean free path is nothing but, yes, that is nothing but average distance between two successive collisions. So the D for water vapor is same as that of air, that D diameter. The number density is inversely proportional to absolute temperature. So we can write N is equal to 2.7 into 10 raised to 25 into 273 by 373, which is equal to 2 into 10 raised to 25 per meter cube. So that mean free path will be equal to 4 into 10 raised to minus 7 meter. Okay, here mean free path is 100 times the interatomic distance, that is 40 Armstrong, and it is large value of mean free path that leads to the typical gaseous behavior. Gases cannot be confined without a container. So, using the kinetic theory of gases, the bulk measurable properties like viscosity, heat conductivity, and diffusion can be related to the microscopic parameters like molecular size. Okay, seeing is believing. What is this seeing is believing? This is just for information. See, can one see atoms rushing about? Almost, but not quite. One can see pollen grains of a flower being pushed around by molecules of water. The size of the grain is 10 raised to minus 5 meter. In 1827, a Scottish botanist Robert Brown, while examining under a microscope pollen grains of a flower suspended in water, and noticed that they continuously moved about in a zigzag random fashion. So, kinetic theory provides a simple explanation of this phenomenon, which means any object suspended in water is continuously bombarded from all the sides by that water molecule. Since the motion of molecule is random, the number of molecules hitting the object in any direction is about the same as the number hitting in the opposite direction. So the small difference between these molecular hits is very negligible compared to the total number of hits for an object of ordinary size, and we do not notice any movement of the object because in opposite direction also the same number of hits it will take. In one direction the number of hits will be equal to the number of hits which are taken in the opposite direction because that water molecules move randomly. See, when the object is sufficiently small but still visible under a microscope, the difference in this molecular hits from a different direction is not altogether negligible. If the water molecule is very negligible, then we can't neglect that. That impulses and the torques given to the suspended object through continuous bombardment by the molecules of the medium, that is water in this case, do not exactly sound to zero. There will be a net impulse and torque in that direction, and the suspended object moves in a zigzag manner and it tumbles around randomly, and that motion is called as Brownian motion. It is a visible proof of molecular activity. So, in the last 50 years or so, molecules have been seen by scanning, tunneling, and other special microscopes. In 1987, Ahmad Zewail, an Egyptian scientist working in USA, was able to observe not only the molecules but also their detailed interaction. He did this by illuminating them with flashes of laser light for very short durations of the order of tens of femtoseconds, and photographing them. One femto is nothing but 10 raised to minus 15 seconds. Okay, and even one could study the formation and breaking of chemical bonds.